tie hole in this one. Let's take a look at finding a limit that looks like the limit is x goes to positive infinity of the square root of 1 minus x squared. Let's see what happens here. So before I do anything else, let me just make a graph here. A graph will be very instructive in terms of understanding the limit. So let's make a graph. This is going to be my x-axis. This is going to be my y-axis. Let's add a picture. Now I know, because I've done this enough, that the square root of 1 minus x squared, this is a positive here. It's basically the top of a circle. So let me draw in the top of a circle here. That'll look like this. Let's erase the bottom. We don't exactly need that. I don't want it to be getting in the way of our work. And then let's just zoom in on this a little bit and ask ourselves a question. So for example, what happens here in the following cases? Let me grab an arrow. When you input this value of x, what you output is a value on the y-axis. It's not a problem, see? Or you input this value of x, what you output is a value on the y-axis. It's not a problem. But then what happens, for example, in this particular case? When you have, let's say this is 1. So then 4 spaces more. 1, 2, 3, 4. But this here would be a 2. What happens when you put 2 into the function? Well, let's calculate it and see. So I'm going to have 1 minus 2 squared. When you work this out, that's going to be 1 minus 4, which is going to be, let me zoom over, negative root 3. So that's going to be the root of negative 3, which you very likely know, once you pull the I out and all that, is I root 3. So in this case, when you plug positive 2 in there, obviously you are not on the graph anywhere, and the output is a complex number, I root 3. You can imagine that if you did this one more time, so let me count another number of spaces here. About here, let's say we plug 3 into the function. Let's see what we get as the output. I'm going to have 1 minus 3 squared. That's going to give me the root of 1 minus 9, which is then negative 8. Under the root symbol, you simplify that, so that's going to give you 2 root 2i. Just like the other one can always be written to, remember, as the root of 3i this way. So both of these outputs contain I. And obviously the reason is these points that we are plugging in are not definitely part of the domain of the function. The domain, the allowed values, would be these ones here. Let me grab that and emphasize this. This would be from here to here, and then it would stop here. That would be the allowed domain. So the question is, what happens over here when you take the limit as x approaches infinity of the expression square root of 1 minus x squared? Well, you gotta transition to I to find the limit. And let's see what happens. You can tell by looking over here at these outputs that this is the root of 3i, this is 2 root 2i, and if you continue to do this process, let's just exaggerate it one more time with one more value so we can build up our intuition a bit more. So instead of using 3, let's see. I'm gonna just cut this off slightly here at the very end. Alright, I terminated the arrow. Let's continue over here. Let's do it one more time. So 3 and then another 4 spaces. This will be a 4. So let's calculate the value of 4. So I'm going to have now 1 minus 4 squared. So that's going to give me 1 minus 16, which then will be the square root of negative 15. So this value is going to be the root of 15 and then I. And I hope you can tell just by looking at these, the following is true pretty much. That first you have this value right here. And then you have a bigger value, this one here, and then you have a bigger value, this one here, but they all contain I. And because of that, what we can state essentially is the following. If I were to represent the outputs when x is a value beyond 1, so these values that you see here, all of these values where I'm tracing, these are all beyond 1. And the outputs then all contain I, the way you see it. So for that reason, what we may want to do is add a new graph to understand this better, and that new graph, let's say, will contain the following. Let me add that here. It's gonna have a real part and an imaginary part. So this is going to be my real axis and this will be my imaginary axis. Let me zoom in on this. Let's label things. So in this context, perhaps you've seen this is RE for real, and then this is IM for imaginary. And the outputs from our function over here, when x goes towards positive infinity, are complex values. So in this context, you can do the following, say. I'm going to call this I. This is going to be 2i, this will be 3i, this will be 4i, this will be 5i, this will be 6i, and it's gonna go up there towards positive infinity along the I-axis. So you have to indicate that somehow. Let's do it this way. What I'm gonna do is I'm gonna add a kind of squiggly over here, and then this way. And the squiggly is meant to suggest that we're skipping values, but we're going towards this infinity up here, which is I times basically infinity. So infinity along the direction of I, which means that our limit using I can now be found. If you look back at the actual calculations we did down here, first we had the square root of 3i, then we had the 2 times the root of 2i, and then we had the square root of 15i. So these values are increasing. Roughly speaking, I would plot them along this vertical axis. So the point is that they're going in this direction. Let me emphasize this key point. Our values are going in this direction, like that. They're increasing. So over here, if I were to write the limit value, of this limit, I would simply write that it's I infinity. That's the value of the limit. Let me zoom out. So that's it for this one. Thanks so much for watching. Please leave a like. It all makes a difference. I appreciate the fact you're here, enjoying these little journeys with me. I'll check you out in another video.